Hello everyone, I'm Li Xin. Today I'm going to talk about perspective-aware urban scene parsing. And this work was done when I was a visiting student to National University of Singapore. Parsing urban scene images benefits many applications, especially self-driving. Images are captured by car-mounted cameras, and predicting the category of each pixel enables the self-driving cars to perform reasoning about the overall scene background. Based on the deep learning, various approaches have been proposed to refine predictions and to deal with heterogeneous object scales. Some algorithms try to refine predictions by exploiting feature maps output by more bottom layers. The multi-scale training and testing is also employed for better performance. However, these generic parsing models treat all scales and locations in the image equally and do not consider the geometry property of car-captured urban scene images. As captured by egocentric cameras, a nearby car seems much bigger than a car far away, and the distant objects with small scale usually crowd together around the vanishing point. We trained a baseline FCN model on the Cityspaces dataset and observed that there are two typical types of parsing error. First, the model do not perform well on parsing distant small objects, that is the boundary error. Second, it tends to break down large nearby objects into several pieces of similar classes, that is the broken down error. To quantitatively analyze how much perspective distortion affects urban scene parsing, we split the image into central region and peripheral region. First, we find that the performance in the central region is much worse than in the peripheral region, especially the object category. Second, if we delve into the vehicle category, the IOU class deteriorates largely in the peripheral region, which can be attributed to the broken down error. Both of these two problems are from ignoring the perspective geometry. So our first intuition is to locate distant small objects and have a refined parsing result. To this end, we propose a perspective estimation network. We use the object scale as a clue to roughly estimate the perspective geometry. The ground truth perspective score for each pixel depends on the ratio of category level average instance size over the real size of this instance. By such definition, an object smaller than the average size of the corresponding category will be given a larger value in the perspective heat map. The PEN has a same structure with baseline FCN model and is trained by minimizing a smooth L1 loss. With the produced perspective heat map, we can localize the region with maximal response, which is referred to as FoveaNet region. We give a qualitative comparison between the single image depth estimation and our estimated perspective heat map. It shows that the perspective heat map can produce a much more detailed prediction and thus better localizing small objects. Now we introduce our perspective-aware parsing network. Based on the heat map, we can localize a FoveaNet region where small distant objects crowd. Then we perform scale normalization on the FoveaNet region, on which it produces a finer parsing via the FoveaNet branch FCN model. This result is infused with the parsing from the cause branch FCN model into the final prediction. In this way, small distant objects are untangled from large near objects for parsing. Here we show the performance of our perspective-aware parsing network on the Cityspaces dataset. First, we compare the FoveaNet region estimated by PEN with a fixed FoveaNet region, that is the yellow rectangle and the red rectangle. It shows that PEN better localizes the regions covering small-scale objects and is adaptive to different images. We visualize the parsing results on the FoveaNet region with FCN baseline model and with our algorithms in the third row and the fourth row respectively. One can observe that perspective-aware parsing gives results with richer details. This is also confirmed by the qualitative result. And our algorithm performs better in parsing small-scale objects, highlighted in green and blue in the second row. The second metric, IIOU, gives greater weights to parsing small-scale objects. Now, Another issue is the broken down problem of large objects. Intuitively, we can apply dense CRFs to smooth the prediction, at least the brown number in the third row. However, directly applying dense CRFs tends to oversmooth the prediction on small objects, at least the yellow number, because it's unaware of the scale variance within the image. So we propose a perspective-aware CRFs that consider auxiliary object detection results and perspective information provided by PEN. We aim to alleviate the broken down problem and meanwhile avoid oversmoothing the details. Formally, we follow the deep lab model and multiply the pairwise potential with a new spatial support compatibility function. The object bounding boxes decompose dense CRFs into several smaller ones. And among the bounding boxes containing pixels Pi and Pj, the box with maximum detection score, DK, is selected as the target one. And this mu incorporates perspective information as follows. It lowers the weights of the pairwise potential at the bounding box with higher heat map values. Thus, for a small object with high heat map value, the pairwise potential becomes small and the unary potential plays a major role. Now we give some additional parsing examples from the perspective-aware CRFs model. The object detection provides several high-confidence object bounding boxes, and the baseline FCM model tends to break down large objects into several pieces. By considering auxiliary object detection results and the perspective information provided by PEN, the proposed CRFs model effectively alleviates the broken down problem and meanwhile avoids oversmoothing the details. This is also confirmed by the qualitative result. The perspective-aware CRFs alleviates the broken down problems and meanwhile avoids oversmoothing the details highlighted in red in the fourth row. We have also made a comparison with other competitive models on Cityspaces test set, and FoveaNet outperforms other competitive models. So here's the summary of our FoveaNet model. It explicitly takes perspective into consideration. The perspective-aware parsing network aims at better parsing distant small objects by localizing where they crowd with a perspective heat map. The perspective-aware CRFs aim to alleviate the broken down problem and meanwhile avoids oversmoothing the details. Thank you all for your listening, and my poster ID is 4, and welcome to make a discussion. Thank you.
Are there any questions? Any questions in the other halls?
No questions means I've done a good job.
No. I was wondering. Sometimes small objects. So this is a really great idea, by the way. Sometimes small objects appear not actually physically far away, but fairly close. Have you thought about this issue?
Yeah. So. We can't solve all problems. We need to solve the major problems. Sometimes because our perspective estimation network directly optimize the performance of localizing small objects. So based on the experiments, based on the results, we observe that most small objects are distant small objects. Yeah.
Okay.
That's our motivation.
Okay. Well, let's thank the speaker again.